Hitchin and Moore-Nekrasov-Shatashvili.
Yes, that's correct, but in fact the question is well, the title is actually a very good question. I was, the way this talk came about is it will be rather informal. The way it came about is that actually Anton wrote to me, is it okay if this is the title of your talk? And so, yeah. so then I slowly converged to understanding what I was supposed to say. So, and I'm still not there, but vaguely I have an idea of the general direction. So, by the way, so this is, of course, a very important, beautiful work by Moore-Nekrasov-Shatashvili. It's the year is 2000, I think, or 1999. And just about the same time, I was working with Tamás Hausel on intersection theory of Higgs moduli spaces, and so this is the subject towards which we are trying to converge. So let me start somewhere at the beginning, somewhere in the 60s, 70s. Of course, a central result in the subject is the theorem of Narasimhan-Seshadri. Narasimhan, maybe there's no H. Seshadri. And it is the following. Suppose we are trying to solve the following moduli problem. We are trying to classify rank 2 bundles on a curve. So I'll take a curve. It will be genus G in general. And I'll fix an auxiliary bundle psi on the curve. And it's a line bundle of degree 1. Say that's the only thing is important, and it's odd degree. Then we can define, what we would like to do is to classify, so I'll denote by n, we would like to classify rank 2 holomorphic bundles on the curve. So this is now a projective curve. This is in the language of algebraic geometry. So these are rank 2 bundles, and it's the determinant line of this bundle is going to be isomorphic to this fixed one. And actually the space doesn't depend on this psi, so that's why auxiliary. So we'd like to classify these objects, and then this is the work of, basically it's a work of Mumford, the basics of GIT, which says that you cannot classify all of these, but you can get a very nice space if you fix some condition of stability. And the condition of stability in this case it's the following, is that it's a rank 2 bundle, so you can look at all of possible sub-line bundles of these vector bundles. So this is a line bundle. And the condition on V is that for all these line bundles should have small degree. It cannot be a large degree line bundle. So in this case, it just means that it's a non-positive degree. So I look at this set of bundles, and well, I divide by the obvious isomorphism. I look at this set of bundles, and then this space is good. So now this is in the category of algebraic varieties. It's a projective, so that means compact, dimension 3g minus 3, projective 3g minus 3, smooth. That's what I wanted to say, smooth variety. Okay, and so then our goal is to study these sorts of varieties, these sort of moduli spaces. So the theorem of Narasimhan-Seshadri links this to symplectic geometry, to the symplectic situation, it says the following, is that we can construct another space, the space n, I don't know, hat, and this is going to be just the representations of the fundamental group of C minus a point P, which we are going to fix here. P, and I'm going to say, I'm going to look at representations from here to the group SU2, and I'll fix the monodromy around P. So this is some gamma, and the gamma of this loop around P is going to be the matrix minus the identity. So we look at this, and then so this is as we can write this as a so this is by the obvious identity of isomorphs of representations by conjugation, but I'll write this down now more explicitly. So more explicitly, it is that we just look at some matrices AI and EI, which are in SU2, and then I'll write and get it down explicitly. It just means that I look at the commutator A1, B1, etc. AG, BG, sorry, this I goes from 1 to G, and then AG, BG equals the identity. And I look at this linear algebra sort of problem. These are commutators of matrices in SU2, and I divide by the adjoint action of the group SU2.
Minus identity, right?
Right, so identity, but it's minus. The identity is still the same thing, that's right. But the minus didn't fit on the blackboard, so I said plus. It's an informal talk. So this is a well-defined set. Now there's no categories, anything. And so the claim is, so it turns out this is also a smooth, now it's a symplectic, real, obviously it's not the same thing. It's a symplectic manifold. You can define a symplectic structure on it of dimension 6G minus 6. Real, of course, this is real dimension. That was complex dimension. And the claim is that these two spaces are isomorphic. So this is the Narasimhan-Szenes theorem. So this is a key philosophical result also, which goes all the way through many different aspects of mathematics. Tian's work on the idea is that these two things are related, actually. The fact, so here, I motivated this fact that stability we need so that we have a variety, but actually the point is that stability has to do with kind of a metric condition, you know, this SU2 thing on the bundle. So these two things are somehow related. This equivalence goes much further, and this was one of the first very unexpected effects of this. And so, of course, when you study the topology, then both of these points of view are useful. So I kind of like this one a little bit more, but there's no reason. Well, there's one reason I'll explain today. Now, so now what are the invariants, the formulas we are talking about that we would like to be studying? So from this point of view, there is the way this works out is that there is a universal bundle, what's called N on N cross C, and the classes of this universal bundle generate the cohomology and the of this space N. So I will not say what precise universal bundle is, but it's the obvious thing, so I will not define it precisely. So it's a rank 2 bundle, which for each slice at N gives you a bundle isomorphic to what it should be. So this is a tautological or universal bundle. Usually it's called universal bundle. So it exists, it's not completely well defined, so you need to take classes that are well defined. But I will actually just talk about volume, so this is a relatively simple thing. So this has there's a relatively simple way to define. So for example, if you normalize it correctly, then from here you can define a line bundle L, which will be just say the determinant of U at some point P. Okay, and so then this will be a line bundle on N. This requires some correct normalization, but we'll assume we normalized this U correctly, so it's not unique. And so the question, so this line bundle is what will play a major role. On the other side, of course, since it's symplectic, that's much more natural. You do have a symplectic form omega here. And so then we will be interested in, so when you have this line bundle of smooth variety, it's actually, you choose the ample one, then it's a natural invariant to look at the say the H0, the Hilbert function related to this line bundle, which is, let me call this M, which in this case, because it's a Fano variety, this is actually the Euler characteristic of this line bundle, which is given by an integral, so the integral of C1, so sorry, E to the M times C1 of L, so this is the first Chern class, it's exactly that symplectic form, omega, multiplied by the Todd class, which is some non-homogeneous characteristic class of this variety. Okay, so for now, what the thing to pay attention, I mean, to register is that this is, of course, once you do the intersections, so the M here is a sort of a variable, this will be a positive integer polynomial in N. Okay, so that's kind of obvious from this formula. So this is what's called the Hilbert polynomial of the moduli space, and this is an important invariant. Maybe just one little remark I'll fit it in here is this is a positive integer polynomial in M, and of course its leading term is precisely what you would call the volume of this space. So the leading term of this polynomial is equal to so this I'll register this coincidence here already, is just going to be equal to 1 over the dimension of the moduli space factorial times the integral of omega times to the power the dimension of this space, which you would call the volume, symplectic volume. Okay, so this observation then played a big role in this whole thing. So now let me actually, now we start, I think that's a nice time to start with the formulas. So the first formula, I'll write down the formula for this polynomial. Okay, so I'll start with that. So for now, this doesn't play such a big role, these two things. Later, when I pass to Higgs bundles, the situation is much more serious. I mean, then these two things become, so it's much less understood. For now, it really doesn't matter. You can think of it this way or that way. I kind of like this one a little more. So formulas. So let's see. Well, let me just write down first the formula itself. So the form, this is equal to the following amazing thing. This is what's called Bernoulli's formula. Bernoulli formula. I don't know why it's Bernoulli. It's usually called Bernoulli formula. And it's the following. It's the sum. J goes from 1 to 2m plus 1. And here I put minus 1 to the j, and then it's m plus 1 divided by the sine squared of j pi over 2m plus 1 to the power g minus 1. So that's our first formula. And I have to say, this is one of the most amazing formulas I ever seen in my life. I was just lucky to become a graduate student when this was invented in '88. So I became a student of bot exactly this year. So this is an absolutely stunning thing. I mean, one of the kind of slightly exotic feature of this formula, that in fact it's not clear that this formula is positive, integer, and polynomial. None of this is clear actually, and it required, I have to say, we'll get to Witten's results, etc. And in fact, even he didn't have I mean, it was not, there's no direct proof of this except for the obvious thing that these two things coincide. And even I gave this to Zaghi at one point to ask him what he could say, and he got very excited, and he actually could prove that this is a rational number, but to prove that it's an integer or it's positive, he couldn't prove, obviously not using the topological field theory, but just using number theory. I mean, it's actually not at all clear. Okay, so this is one form. So today I will not speak about proofs at all, so I'm just going to look at the question is what the formulas are. So this is one formula, and then of course this was the idea. So this is I won't write names today maybe, but it's the Thaddeus-Verlinde-Witten package. The idea was precisely to use this correspondence, the fact that it's a leading. So this was the very first result, Verlinde's, and then Thaddeus found the well, that was his thesis, I think. Found the leading term and then other intersection numbers using this formula, and found the whole intersection ring in some sense, or at least the volume in any case, and found out that they are actually Bernoulli numbers. So let's get to now this volume formula. So so the formula for the volume, actually it's not so difficult. I mean, that's what Witten also did with this, is that what you want to do is to just kind of look at since it's the leading term, you just let m go to infinity and you see what happens. And if m goes to infinity, what happens is that you kind of, you scale this out and you just see sine becomes approximately 1 over j, and you get the following formula that it's up to some constants. So I apologize, these constants I might not get right. But this volume, well, here you can actually just calculate what it is, up to this factorial, etc., is just omega 2. I'll just write top for this volume, for the dimension of n, is equal to, so it's up to some constant, which you can calculate from here. It's the sum from j going from 1 to infinity, minus 1 to the j, and then, sorry, what am I saying? Minus 1 j, yeah, 1 over j to the power 2g minus 2, right? That's what it is. Okay, so that's the volume of the moduli space. Well, I said modular constant that you can easily get from here. Okay, so this is our second formula. So and that's our plan, is just to go between these generalize now these parities. So so the talk about formulas like this and formula like this, and just explaining what's happening. Chalk is kind of they exist. It's recycled chalk. It's chalk that people rejected already because it was too small, and then the usual thing you go through it. So anyway, so let me just do the generalization. So one generalization is not really fully necessary, but I kind of like it in a sense. It was an important idea in any case, is to pass to the, if you like, the parabolic case, or what here it means that I look at other orbits, not just minus 1. So the first generalization is this parabolic case, for which there is also Riemann-Szenes correspondence. So in the parabolic case, I'll just be very quick. I mean, roughly what you're doing is that you look at the space, in fact, PUP in here roughly. Okay, so this is a P1 bundle of obviously it's a rank 2 bundle. It's a P1 bundle on N, and that's called the parabolic moduli space. And the Narasimhan-Seshadri theorem says that this is equal to, this is isomorphic to the same thing. So you have these commutators, but then here you put, well, you can put some e to the, yeah, so the matrix, say, e to the x, 0, 0, e to the minus x. I think something like, or maybe ix, right? Maybe there's a pi that I'm not going to get right, okay? But, you know, it's that. And then, of course, you divide now by the stabilizer, or something like that. Or this matrix. So it's exactly the same construction, but you replace minus the identity. Or you could say that you take the orbit of this element to divide by the adjoint group. It's the same thing. Okay, so is this clear? Yeah. So maybe I didn't lose. So the point is that why this is isomorphic is that, of course, this does not depend on x. So x is between 0 and, well, in this case, it's 0 and, say, pi, something like that. Okay, so if x is between 0 and pi, then topologically this space doesn't depend. I think so that's why here I can identify with the same space. But in fact, in the symplectic side, it's a little bit more interesting because there is actually a symplectic form omega x on this space. So this becomes a little more interesting. So let me write down now the formulas for this case. So the formula for this case, they look as follows. So I use, instead of m, I use k. You'll see why in a second. So it looks like this. There is a line bundle here now. Instead of L, there is a line bundle which will go LK lambda. And then which is concocted. I will not exactly explain now how from the L that I defined here, which is pulled back from this N, and the O of 1, the line bundle coming from that thing. So the formula looks like this. So again, this Euler characteristic of n LK lambda is equal to, and now you get something like this. It's the sum. So it's let's call it n equals 1 to k plus 1. It's very similar. You will have the same story, k plus 2, and then 2 sine squared j pi k plus 2, or n pi k plus 2 power g minus 1, and here you put chi lambda at this point, j pi divided by the same one that you have. Sorry, I confuse this all the time. N pi k plus 2. Where lambda is the highest weight of this corresponding SU2 representation. And so as I said, lambda comes from the sort of the O1 side of this. So you have a formula like this, and you have a corresponding, again, you can calculate the corresponding volume. So this kind of x is sort of the ratio of lambda and k, really. And you get sort of a more general formula. So here, I will be a bit more precise about this. So if you like, well, let me just give you my sort of his favorite picture. So the way it looks like is that, so this is a bundle over this. So the bundle, so this L is somewhere here, and then the lambda is kind of in these horizontal directions, right? These lambdas are here. Okay, it's actually lambda here. So I'm drawing sort of the H2 of this space where the line bundles are in that direction.
I must say that this picture I don't quite understand. What is this picture?
Okay, so let me explain it. So So here, I didn't say this here, but actually H2 is just Z here. Okay, so it's just one line, one direction. When you take something that H2 is Z, when you take a P1 bundle on it, you get another direction. So now H2 will be two-dimensional. And roughly, this L is the same L as I had here, it's this. And the other one, there's an element here, which is just the O of 1. So it's the tautological lie bundle of this P. So I'll call that O of 1 in algebraic geometry. So that's the picture. And then, so these two parameterize a lattice. But you think of this as level 1 and this is level 2, and then the lambda is just between 0 and 1. Okay. All right. So let me now go to the volume form here. So the volume form here then, so the integral of over this PUP, which is the corresponding space here, of this e to the omega x is equal to the Bernoulli polynomial, again up to some constant. So it will be equal to b2g minus 1 of x. Okay, where b is the Bernoulli polynomial. So this is b of n. X is just equal to the sum of e to the 2 pi. So maybe I should have multiplied it by 2 pi. 2 pi I and x divided by, no. Let's do this up now. J to the n. Okay. So this is famous Bernoulli function given by simply by its Fourier series, one for each n, and then it's a fact that this is the polynomial, and this is exactly this polynomial for 2g minus 1. And you can recover actually my previous formula roughly, takes a little effort. If you make x to be equal to 1/2, so that this is pi, then you exactly find this form with these signs that I have, with these signs here that I have. And then there's a shift from 2g minus 1 to 2g minus 2, which comes from the character form. So this is our first generalization to the parabolic case, and then so I'll go now to the any higher rank case. What do I do here? Is there a clock here? No. Okay, well it's good. Okay.
Roughly.
Yeah, half.
Yeah.
Okay. So now higher rank. And so higher rank, there really isn't very different. So the way I set things up for mostly this is okay. So when you do this higher rank situation, everything just carries over. The stability condition is slightly different. This doesn't change at all, except here you need to put another central element, and here you put just other orbits, so it's the same thing. Okay, and the formulas are also pretty similar, so let me explain how the higher rank formulas are. So maybe let me explain this one, but it's almost the same. So the higher rank case, so is the following. You will have say key n Lk lambda. So now you will have a sort of a similar situation, but you know the lambda will be now a weight of the higher rank group. So there's more dimensions if you like. Okay, so this is now will be the so to define this, I will. Well, maybe you know what? Let's just do rank 3. Okay, so the formula for rank 3 is the following. So you have something like, I'll define a finite set of points now, which will be Sk, which is, now I need to define it. It's really naturally this set of points over which we sum, it's the set of points in the regular part of the maximal torus of of now the group that you're looking at. You can replace it by any other group, and you set t to k plus, here this famous dual Coxeter number, which is 3 in this case. K plus 3 is in the center of SU3. Okay, so this is the natural set of points divided by the Weil group of SU3. But as I said, you can replace SU3 by any group. This is the set of points, or you take the sum. And then what else? You need this form is just a power of the Weil denominator. So this is just delta, which is equal to the, well, in this case it's just product of 1 minus t to the alpha, for alpha are positive roots. So in our case it's just something like 1 minus e to the x, 1 minus e to the y, and 1 minus e to the x plus y, or t, or so, well, yeah. Okay. And what else do I need to tell you? And well, I need to limit actually again the weights. So this lambda, which is the weight of the group highest weight, dominant highest weight of SU3, will be just a pair of numbers, such that I mean, they're generated 0, lambda 2, and lambda 1 plus lambda 2 is less than k. But this is not so important. This is just for which formula or for which values this is true. And then the formula is the following, is just a sum here over all points in this set SA, on this finite set of points of finite order whose power is in the center, and then you have high lambda of p, and then here you have 1 over delta to the power 2g minus 1, something like that. Okay, so it's a complete analogy. With that one, obviously, the formula there is, well, anyway, it's the same. Okay. So this is our general formula. Now, one point is that my approach to this, so I didn't explain this at this point, to understand the polynomiality, so this is one important point, is to represent this formula by a residue. Okay, so let me do that here. So let me erase this. Let me erase this. Okay. So a little remark here about residues. So a residue formula here, it looks as follows. So just a second. So maybe let me do. Sorry. Yeah, maybe let me do the rank 2 case. Sorry, I'll do this one. So this looks as follows. It's the residue at t equals plus minus 1 of the following function. There's some constant again, and here you have t to the lambda plus 1, t minus t inverse to the power 2g minus 1, and then 1 minus t to this big 2k plus 4 dt. Okay, so this is just some very elementary way. It's a differential forms whose poles are exactly at this point sk that I'm describing, and this function is precisely this function, and then you just apply the residue theorem for the complex plane in this variable t, and you exactly recover that. So this will be crucial actually. So one important feature of this formula that here, once you make an exponential t equals e to the x substitution, the polynomiality of this thing becomes evident because you just make an expansion and you will find the coefficients of the corresponding column.
Maybe I forgot this 1 minus t to the power 2k plus 4. Where does it come from?
It's just because you see there's a pi here. So, but you want 2 pi. So there's a doubling for that reason. So it's 2k plus 4 is just twice k plus 2. So, as I said, you see, because there's this center here. So there's a doubling if you really want to do it right. But the doubling is resolved by the fact that you look at tuples. And then the point is that actually the residues of the tuples are the same if lambda is even, and they are 0 if they are not. So there are various, yeah. Okay. And so then maybe here, I can also explain this one will be maybe useful. So let me just continue this here for a second. I'll put this in parentheses. So this formula, I want to give a residue form for this. So let's say it's something like. So this comes from that Bernoulli setup. So it's here I'll write the formula actually. 3g minus 3 factorial multiplied by the residue of 2 over sine 2x, and here 1 over x to the power 2g minus 1 dx, 2g minus 2, sorry. Okay, so that you can get a residue formula. It's basically a sort of a Bernoulli number, but instead of 1 minus e to the x, we have the sine 2x, so that that will produce you these minus 1s, and it's precisely corresponds to this Bernoulli thing. As I said, you need to make x to be 1/2 in that case. Okay. All right. So, and then there's a residue formula for this one as well, but that becomes a little more complicated. So I will not write that, but I'll just write the volume formula. And so the volume formula, and this was the beautiful formula of Witten, it looks like something like this. So for the if I write down the volume formula here, then it will be what I'll call multiple Bernoulli polynomials. Sorry. So it's the integral of omega to the omega k omega x as a vector to the power top is going to be equal to. So again, this now x describes a more general orbit in the group, adjoint orbit in the group. Right? So it's this analogy carries over to this general case, but I don't want to describe precisely the formulas. But on this side, they're exactly the same. It's just you replace it by higher rank group, and you replace this by an adjoint class. Okay. So you get some sort of generalization of these Bernoulli polynomials. So you get the following thing: is that it will be the sum over all the lambdas, which are now just dominant weights. And then you do the following: you just look at key lambda evaluated on this the corresponding orbit x. Right, so this x is now an orbit in the group, so the character can be evaluated, and you divide it by the dimension of the corresponding representation v lambda raised to the power 2g minus 2.
It's high lambda of 1.
Pardon?
If high lambda of 1. Maybe 2g minus 1.
Yeah. Sorry. No, I know what I'm doing wrong. Sorry, I made a mistake. Sorry. You're right. is just e to the yeah, it's just e to the I lambda x like this. Well, the pairing of lambda and x. And then it's 2g minus 1. So if you look, yeah, it's like you have it there. So there's a trick here which is used everywhere, is that, in fact, like I used it here, for example. If you look at this case, you can see this trick. Right? So it's the fact that, of course, this one in general has many terms, and I only kept one term. And the reason for that is that because of the symmetry of this thing, and actually because of the wild denominator form, first you can split off in the wild denominator one factor of this, which makes this, instead of 2g minus 2, it makes it 2g minus 1. And then, so that's why you have 2g minus 1 here. And then because of the anti-symmetry, you can replace this n factorial or whatever terms up there just by one term, moduli constant. And so finally you just have this. So I can replace this character by augmenting by one this thing, and replacing the character by just this. And this is then precisely the same trick here. And so then it becomes a complete analog of this Bernoulli polynomial except, of course, this is the dimension of the corresponding representation. And yeah, so that form becomes a special case of this formula. Okay, so let me try to explain a little bit now about Higgs bundles, okay? Yeah, I mean, this is a little difficult, and maybe it's a bit boring to listen to so many formulas. And it's incredibly hot here also. I understand. So, okay. So now Higgs bundles. And so for Higgs bundles, the amazing fact is that you have sort of a similar analogy. So the left-hand side is a little bit more exotic, but the right-hand side is identical to what I was doing before. So the left-hand side, now I'll denote this by MC, so everything curve, everything's the same. And so here, now I just look at, now I just pairs a bundle over the curve, plus a phi, which is a map from V to, so now I have the curve, and there is a bundle K, which is the canonical bundle, the bundle of differentials. It's basically the cotangent bundle, if you like. It's a line bundle, and the algebraic setup. So it's a twisted matrix, a twisted endomorphism. So you look at this pairs, V and phi. This is what's called the Higgs field. This is the bundle, and then you have a stability condition. Maybe I'll not explain this. It's a similar thing to that. It's not so important. I mean, it is important, but yeah, I don't have time for that. Okay. So this variety is of complex dimension 6g minus 6. And it has, it's smooth. Sorry, so here is the same thing, of course. Wedge 2 is isomorphic to psi, so I keep that. Smooth, and it's endowed with a C star action. Which is just takes phi, lambda phi, to lambda times phi. So it just multiplies this field by something. And it has what is important for us is that the fixed point set of this action, so it's non-compact. But there is some properness condition associated to it. And so then if you look at the fixed point set, that it turns out, well, there's an obvious set which is fixed by this, which is just this NC. So this just corresponds to phi equals 0, right? If phi equals 0, then you can just take the Higgs field is obviously, this is fixed by this action. But it turns out that the stability condition that I would need to specify that would take some time. But anyway, there is some extra fixed point loci F1 F G minus 2, which have the form of like L1 direct sum L2. So bundles that split into direct sum, and then there is this Higgs field acts as a nilpotent matrix on this basis. Okay? So the reason this is finite is because of the stability condition. For now, for the formulas, this is enough to know. Okay. And now we restart again, but of course it's non-compact. Sorry, no, I forgot to mention, yes. So then the point is that this Narasimhan-Seshadri theorem goes into the Hitchin-Simpson theorem, which says that this is isomorphic, but this is really fantastic. It's exactly the same thing as we had before for the non-compact group. So now you just have, this is just the product, so it's just AI, BI, same G things, A1, B1, AGBG is equal to, say, minus that entity. Now you divide by the adjoint action. Well, you have to be a little more careful because so I will double divide by the adjoint action of whatever, SL2C. So now it's SL, sorry. So these are now in SL2C. Okay. Okay, so one important thing is, and this is technically very crucial, is that here we have a circle action, here we don't have a circle action. So here we have a non-compact variety, which is affine action. This is obviously not affine. And so to do any kind of formulas, this is kind of hopeless. For example, volume formulas for now are hopeless. And in fact, it's even now, so the center of attention is to kind of understand the two sides of this thing. And enumeratively, this is kind of unclear. And exactly the Moore-Nekrasov-Shatashvili theorem says something about this. In a sense, I think that's what they want to do. It's a little bit incomprehensible, but anyway, what they want to do. Well, let me describe, so how much time do I have? 10, 12 minutes. Okay, so let me try to describe to you what, so let me see. Maybe I'll just try to do the volume.
My timing is a little bit negotiable, right?
Well, it's very hot though, right? So, so even if you're ready to stay. Plus, I don't know. Okay. So well, in a sense, but let me just write down anyway the two things, but then maybe I'll just concentrate on one of them. So you remember I was doing two things. I was doing, so there is this line bundle L, MC, and let's, that T, of course, will assume, so this is the determinant line bundle. This is a generalization of that line bundle. As you can see, actually, this NC is a subset here in M. So there's a line bundle here, it just extends here, you believe me. Okay. So now, of course, the space of sections is going to be infinite dimensional. So this is not so great. However, if I now look at the trace, the trace of T, which is thought of as an element of C star, so T is C star, right? I denote it by T. T on this, then this could be, in each multiplicity of T will be finite, so this is a well-defined power series. Okay, so this is one of the ways that even though the space is non-compact, we can associate some reasonable thing to it. So that's one point. Now, I actually, technically this is a little bit easier, and you can, to understand what the meaning, or associate a meaning to the formulas. But let me do the other one. So now the volume. So what does the volume look like? So the volume So when I'm talking about the volume of MC, but of course it's the kind of the T volume of MC. The MC is infinite volume, but there is a T volume you can associate to. And so it works as follows: is that you can you can define equivariant integration. And it's the following thing. So we pretend that we do equivariant localization of compact variety, and we write down the corresponding formulas for this thing, as if this was compact and these were the fixed point loci. And then we get something, and this something is going to be a rational function in U, the usual story. So let me just give you a mini example so that it's a bit slightly more clear. So imagine, I don't know, you have P1, okay, and you are trying to calculate the C1 of the tautological line. It's a different L, but it's kind of, so you on P1 you want to calculate C1 of L. Okay, so use the fact that there is a T action here. So if you look at P1 of T, the fixed point set, then it's the north and the south pole. Right, it's the okay, and so then when you do localization, you need to look at the weight of this action. So the weight on the action of the north pole, you get two terms is 1, and the denominator, the weight on the tangent bundle is 2, and then here is going to be plus. This is the north pole, and then the south pole, the contribution, the weight on the line bundle is -1, and the weight on the tangent is -2. So this is equal to 1. So that's localization. And now non-compact. Sorry. So there's U. Of course, the weight. U is the usual variable that you have. And so now, if you do equivariant integration, now suppose you are trying to. Of course, if you sorry. So then, what I wanted to say is that if you replace this by the function 1, so you try to calculate this. Then you get, then it's just 1 divided by 2u minus plus minus 1 divided by 2u. So you get 0. Okay? But now what we are doing actually is slightly worse. We are not looking at P1, we are looking at C. So, and we are trying to integrate, for example, the function 1 on C, for example. Okay? So then it's kind of, in a certain sense, it's a proper space, and its integral is just then what you see here is something like 1 over u. Okay, so the point is to understand, if you do equivariant integration of non-compact spaces, you get some rational functions of weight, of degree, which is minus the dimension of the space. And that's 1 over u is that. And that's what we're expecting to get here as well. And so, maybe I'll need some more. Okay, so that's what we are doing, and we are going to calculate that. So now, in fact, it's easy to see because that's actually, it's not hard to understand. It's a cotangent vector here. So in fact, I'll extend this statement to the following thing, that the cotangent space of NC in MC is an open subset. So that those phi's corresponding to stable bundles form a dense open subset because this is the same dimension now. But the only thing we need actually is that the normal bundle that was relevant here of NC in M is actually the cotangent bundle. So in fact, to calculate this, the contribution, so now we're trying to do the equivariant integration this way, in this setup. So this, I'll denote it this way, the equivariant integral, so sorry, let me just put these circles here. Well, here it's the same, of course. So here it's irrelevant, but here it is important. That's not a real integral, of course. So if I want to do this, then, I don't know, I'll do like e to the omega maybe, or something like that. Then, or some, yeah, let's do this, e to the omega. Then this is going to be an, where this is some class, Then this is going to be a sum over all these components. So actually, it will be a contribution from n, c, and plus a sum of contributions on these sum of contributions from this fi. Okay. And okay, so now formulas, because there's no way back. So let me write down what we get. Okay. And it's going to be, so I would like still, I erased that formula now, but I would like you to still see a little bit of an analogy. Maybe I'll show you what the analogy is with the old volume formulas that we had for this space. But so now this is the rank 2 case, and I'll try to write down what this contribution for NC is. Okay? So the contribution is the contribution is the following. I'll define a differential form, which is kind of it's not so simple. So it's like this: 1 plus 2u divided by u squared minus y squared, right? So sorry, or x. I'll use y. It doesn't matter. So it's just some variable, and the u is the same variable u that I had there. So it's u squared minus y squared raised to the gth power. There'll be a dy here, of course. And then I divide this by e to the y, and then u minus y divided by u plus y, minus the inverse of the same 1 over this thing. So it's like a hyperbolic sign. So it's a little bit of an analog. If I erase this, it's very similar to the way I had before. There was a sign, if you remember, in that formula. There's this rational change. That, and then there is y to the 2g minus 2, there's a u to the g minus 1, a y to the 2g minus 2, and then there's a u squared minus y squared to the power g minus 1. And all this just comes roughly, this modification comes from this normal bundle, from this t star. That's where this comes from. Okay, so I take this. And if I didn't make any mistakes, I now take the residue at y equals 0, and this will be a function in u, and this is the answer. So this is this equivariant volume. So if so this omega is the C1 of this thing. That's what.
Sorry, that's whole thing or contribution of NC?
Oh, sorry, contribution of NC. Sorry, that's what I was. Okay. So I just did this because I never had to calculate everything on NC, and I did it, as I said, the only thing you need to do for localization is this weight that I showed you, this 1 here, and this 2 is this cotangent bundle. And that's some work, but you only do it, and that's what you get. Okay. Maybe, yeah, I overestimated as usual. But anyway, I will just finish in maybe 5 minutes from here. So let me now explain something about a few things about this formula. So yes, so then you go and try to calculate this. And these FIs in principle are much simpler things. These are symmetric products of the curve. So there are some integrals that are much easier to calculate a priori than here. However, there's more of them. But you have a kind of an absolutely stunning fact, which is the following. So let me denote this whole thing now here by omega. So the differential form is omega. Okay? And so the fact is that the sum, you just do the calculation, the sum of the contributions of FIs from I going from 1 to 2g to g minus 2 is equal to the residue of omega at u, or plus minus u. So this is really was a very surprising fact to us. In any case, so we have a final answer. So this equivalent integral is just the residue at y. So the sum for r in 0 and plus minus u of the residue at y equals r of this form omega. That's the answer. Okay? And it's actually very surprising that these spaces look nothing like this and still you get the same thing out of it. Okay, and now, it's a completely elementary thing, which I actually screwed up for 10 years. I looked at it the wrong way, so I explain now some very basic thing, a little exercise. What about, so where are the poles? Suppose you want to do residue theorem in one variable, y, so you use a fixed positive, small positive number, and you want to do a residue theorem in one variable y on the complex plane, okay? So where are the poles? So if you just look at it this way, then, so the poles, so this is sort of the last thing I'll explain, the poles of omega. So maybe like, so now I have minus 1 minute, so maybe just minus 1 more. So if you look, I mean, there is some obvious thing, I just used this, right? So it's clear that we have poles at u and at plus minus, at 0 and plus minus u. I mean, that's obvious. You have this y factor here and the u square minus y square here. So that's not surprising. And then the following thing happens. So, yeah, here we are. So then there is this, this forms poles, yeah, and so the rest of the poles, of course, comes from this fact. So you look at the solution of the, what's called the beta ansatz for nonlinear Schrödinger equation, which is this e to the y is equal to u plus y divided by u minus y. This kind of, there's a squared. Okay? So this is our equation for the poles there. And this is some amazingly interesting, of course, equation, which is central in integrable systems. And, okay, but the question is, let's solve the beta ansatz equations. And so you cannot solve this, obviously, but to study how many zeros does this have, this thing, or solutions. And so what you observe is the following. So there is, for each n in z minus 0, you have, of course, a solution of Bn. So Bn is the pole, such that Bn minus pi I n is less than, pi I, and yeah, less than c, some constants times u. So u is a small parameter when you go to 0. So then what your study is that if u goes to 0, where these poles go. And it's clear that if u goes to 0, roughly this just goes to minus 1, and then you go back to just usual poles, the zeros of sine. And that's why this is the 0 of sine x, so that's not surprising. And so for 10 years I thought that was all. And actually, I don't know what Shatashvili and the Moore-Nekrasov-Shatashvili thing, but actually there is one more pole. And the reason for that, so this is what I'm saying, it's totally elementary, so there's nothing, and it's the following fact, that the following brilliant equality, that this thing here, so let me call this by whatever q, okay? So that q, that e minus, that thing, is just equal to u plus y times tangent hyperbolic of y over 2 and u plus, maybe I scrub the sign, but it's more or less correct, u plus y times cotangent hyperbolic to y over 2 and then divided by u squared minus y squared. Okay? And if you look at it this way, then it becomes apparent that there's one more pole. And this is this pole, so these were Bn for z minus 0, one more pole at B0, which is close to 0, so which is, where am I? Sorry, B0 minus square root of u is less than something c times u squared, something like that. So anyway, it's a pole near 0, but it's outside the u, so it's bigger than this plus minus u because it's square root of u. But it's there. And actually, the way I found this is out because if this pole weren't there, then there would be contradiction with the P equals W conjectures. That's how I found it. Anyway, so I'll finish my talk by the Moore-Nekrasov-Shatashvili theorem, which is the following. They use this residue theorem. They convert this thing to say that since these are now all the poles, we eliminate these poles, so then the result is the sum at the other poles. So the Moore-Nekrasov-Shatashvili theorem just says that this equivariant volume is just equal to the sum over whatever y equals bi. So all the poles are simple and it's some evaluation. And maybe I'll let you do this. So you simply, so this is a simple pole. Well, actually, maybe I'll say one thing about it. Is that is equal to, so a u, so, well, let me just say it. It is equal to a sum, and it's the sum of the residues of this at y equals bi, but there's one simplification because this actually comes precisely as the derivative of, the logarithmic derivative of this, so it's not as complicated as this. So you actually get just bi to the power 2g minus, or b, whatever, n to the power 2g minus 2, and then u square minus bn squared to the power g minus 1. And then here you have this term which they forgot in their first work. I think I pointed out that they're missing it. This factor 1 plus 2u divided by u minus bn squared to the power g minus 1. Okay, so that's the actual Moore-Nekrasov-Shatashvili formula. And I just say two comments at the end. So one is that that's not exactly their formula because they're physicists and they're, of course, they're making sense. And what they're saying is that they want to understand something. Well, it doesn't make much sense, this equivariant volume. So they want to think about some regularized thing. And that actually makes a lot of sense if you want to understand this correspondence, because there's no u here. So you want to associate some integrals, quantities, something to this part. So it makes sense to actually, so what they do is actually they look at the, sorry, there is a 1 over u to the g minus 1 there that I forgot. And so you look at the constant term in u, in fact. And they say of this expression, this function is actually the regularized volume. But this mathematically has almost zero meaning, but I would be really, it would be exciting to find it on the other side, this number. Clearly this is the one that doesn't scale with u, so it makes some sense. So that's the first thing, and the second thing that, of course, just not to make it completely pointless that I introduced all these higher rank things, because we have formulas that, of course, I will spare you of those to some extent. So certainly this thing is done for any, and they also did it for any group, so that's fine. But like this thing, so as I said, I'm already not sure that they knew there is this pole there. So solve the beta, even to kind of vaguely solve it, to know how many solutions there are, I mean, for this beta ansatz equation, and do an analysis and this kind of residue analysis, I don't think anybody knows how to do that for now. So so I'm thinking about that now, sort of how to, for even rank 3. For example, I don't know if you can make it this small. Yeah, so anyway, so this is the complicated analytic problem that is.
Thanks a lot. Questions or comments? How is it if they didn't know about that pole? You say that's their result, but they were just saying it's a sum of the solutions.
Oh, sorry, yeah. So of course I didn't say, as I said, I was not going to talk about proofs. So of course they did it totally differently. They did it like Witten did his formulas by some, so Witten of course used some relatively reasonable Feynman integral or whatever, what do you call those integrals? Path integrals. Now they use some totally unreasonable path integrals because something is non-compact even for the physicists in this case. So and they arrived here and what they did find, they do some kind of Fourier, so it's some sort of Fourier analysis that you do. I mean, you localize somehow some Fourier Poisson form, something like that, and they did find that this volume should localize on these solutions.
Oh, but you say.
And then they made a mistake. That's all. I mean, they found roughly something, but then they made a mistake when it just got that it localizes, but they forgot the determinantal term. You know, when you do these delta functions, there are these determinant, and apparently even physicists make mistakes with when they have to get, you know, the derivative of a delta function, something in multiple variables, and so they forgot this. Yes.
But you're saying their result, they didn't know about this extra pole, but their result was...
Oh, no, I'm sorry. I'm just saying I don't know if they do. No, the result is that it localizes at the solution. So the form is correct. I'm just saying that, because you see, you do, obviously, yeah, you write something, but as u goes to, so the problem is the following. As u goes to 0, these bn's go to the solutions of this e to the y, and then there's this the 0 solution, but then there is already a pole at 0. You see, so this is an additional unexpected pole. You already have a pole at 0, plus at all integers. And then there's another pole near 0, which is relatively big actually, it's squared. So.
Well, how is it?
They just said all solutions, whatever that means.
You found an extra unexpected pole. But now, do we know there are no others? Or maybe
Yes. No. I for rank 2, I have the thing totally down correctly. Their formula is correct. I mean, this correction is correct. They just say, I think, the sum of all. I'm just wondering when you say that. Of course, since they are near the integers, you kind of have an idea how many things you sum over. So the question is, did they know that there is and not only so there's the poles on. Because you see, okay, so put it differently. When you do the volume, so when you cover this up just for n, then you do residue at 0. And if you do Witten's form, they start as I wrote at 1, 2, 3, 4. So there is nothing near 0. It's the residue formula. You understand? It's at 0. You replace the integers by 0. That's what you do for the trigonometric case when you do the usual. Which I did at the beginning, right? There was this sum from what? So then you do this Higgs deformation, so you think you deform these integers at pin by bn. You think you're done, no? I mean, why would there be anything else if in the volume case there was nothing? Exactly the 0 is already, that's where you go, right? And it turns out there is an exotic pole. And so these exotic poles, so that's why I was also very optimistic about my project with Tamás, which then became much more difficult with this thing. So, and then for higher rank, I don't even know what they are. So.
Okay, any more questions?
Yeah, so the original variant, the formula is associated with the fusion category. And how about all these very complicated generalizations? Is there any?
No, nothing is very, I mean, there's only one very complicated generalization. There's no many, it's just one, the Higgs. The other one, so I only spoke of 2 things, and they are before, the fusion thing was actually the more complicated, and the simplification is the volume, so that was the beginning. Now there's this complication, which is this equivariant case. I skipped, I had the equivariant in the formula, which exists. We have some formulas for that. And there is still millions of things to do. I mean, yeah, so yeah, you can calculate them, but there's still, and you still have to come to algebraic beta ansatz, some trigonometric version.
Category.
And no, so this I would be very, yeah, I would, so there is people saying things, but finally, it's not clear. So that's one of the things that I want. I have some things for I know it for, to some extent, I know the fusion algebra for rank 2, but I don't know how to do it for higher rank. So that's actually an interesting thing to discuss.
So there is no some kind of good compactification of the Higgs bundles? There is no good compactification.
Oh, there is.
Whether you can do all the formulas in that compact.
Yeah, that's not a big deal. Yeah, I mean you can do that. Yeah. There is also, I mean, obviously there's the Hitchin map, which plays a big role here, which I didn't want to talk about. And then actually you use that. So there, there's a map from MC to a half-dimensional space, and then you can compactify this space becomes projective, and then MC also becomes compact almost smooth manifold and everything. And then you can interpret these things there as this U and everything as usual intersection numbers in a compact variety, and that's this P equals W thing that we have. You can look at the paper, we do that. The point is now, because these things are not the same, nobody knows how to compactify this thing. So this is like a deadly, this problem is, so this space, which looks much more innocent, is actually much more complicated in every possible way. And so one interesting question is like, yeah, if you have this residue, so an even more complicated thing when you take some constant term of this thing, I'm sure it's somewhere there. So that could be interesting for, I mean, that would be that's where all the effort is actually to link these two things somehow. So they're diffeomorphic, and this seems to be sort of elementary, and so then people try to take some limits of, so the logic is that when you take some limits of some things here, then that should give you something there, or some regularized, but it's much less clear how to regularize integrals there than here. That's the problem. But that's kind of a central thing. Everybody tries to do that in different ways. So this P equals W is of course also that, right? It's something that's obvious here, you found here. That's the weight here. And but there are many other things people try to do, which is related to how to get anything from here to there. So these integrals in particular, that would be very interesting.
Okay. More questions? Well, if not, thanks again. Maybe one short announcement for tomorrow morning. So I think we should